So in this video, I'm going to define a principal ring. So we're going to start off in a commutative ring R, and we're going to use this notation. Bracket A, if A is in your ring, is all elements of the form A times R, where R is in your ring. Now we've seen this notation before in group theory. This notation with the bracket was the cyclic subgroup generated by A. And if you think about what the cyclic subgroup generated by A is, it's the smallest possible subgroup that contains A. It's a similar notation for rings. This notation denotes the smallest possible ideal that contains A. So this bracket notation really, if you think about it, means the smallest object that contains A. So we're going to say an ideal I is principal if I is an ideal of this form. In this case, we'll say that A generates I. Let's do some examples. So here's an example. Let I be the set of functions f in a polynomial ring with integer or real coefficients such that f of 2 is equal to 0. So 2 is a 0 of f. Well, this is really the ideal where we've seen if 2 is a 0 of your function, then your function f can be expressed as x minus 2 times some other q of x, where q of x is in your polynomial ring. This is an ideal of the form A times R. Here's my A and here's my R. So this is my ideal generated by the polynomial x minus 2. This is principal in the ring of polynomials with real coefficients. Okay, let's do another example. So let's again deal with polynomials. Why not? Let's look at polynomials. Maybe this time I'll say we have integer coefficients. And I'm going to add the condition that A0 is even. So the last coefficient, the coefficient of the constant term, has to be an even number. So then I is indeed an ideal in the integer ring, a ring of polynomials over the integers. That's because, and I'm not going to check the details right now for you, but it's really not that difficult. If you take a polynomial with an even last coefficient and you multiply by any other polynomial with integer coefficients, you get a new polynomial where the last coefficient is even. So you can verify directly from the definition that it is indeed an ideal in this ring. But I claim that this is not a principal ideal. So I claim that I is not principal. Why not? Well, let's suppose it was. What would happen if I was generated by a single polynomial f? Well, then one of two things happens. Maybe the degree of f is 0, meaning that f is just a constant term. So f is just simply a constant, like A. If that happens, A has to be an even number because it has to satisfy this condition. then every polynomial in I would be a multiple of your even number, and x plus 2 would not be an element in I. You couldn't get x plus 2 because x plus 2 is not a multiple of a single even number because the coefficient in x is odd. So that's a contradiction. So in other words, the degree of f cannot be 0. If the degree of f was bigger than or equal to 1, that would mean every element in I has degree bigger than or equal to 1. Elements in I look like f times more things. When you take a polynomial and you multiply by another polynomial, the degree could only go up. It can't go down. So that means 2 would not be in I, and 2 is definitely in I to begin with, so that's another contradiction. So this shows that I can have an ideal in a polynomial ring that is not principal, or I could have an ideal in a polynomial ring that is principal. And we'll give a surprising theorem about this in our next video.